Okay, let's pick up where we left off. We left off talking about the scalar product, the vector sum, vector difference. So literally we were just adding and subtracting component by component with the sum and the difference. And scalar multiplication, you're essentially just distributing through, maybe changing the direction of the vector if you're multiplying by a negative, making it longer if you're multiplying by a constant or a scalar that's larger than 1, making it shorter if you're multiplying by a scalar that's less than 1. But let's talk about the dot product, because the dot product is a pretty cool little quantity here. So here's what the dot product is. The dot product is actually a scalar. Okay, it's a plain old number that contains information about the magnitude and the direction of both of the vectors that were used to produce that dot product. Sometimes you'll call the dot product the inner product of the scalar product. It depends on what textbook you're using and things like that. And the dot product is actually pretty easy to get. So if I'm finding the dot product of A dot B, I'd multiply the two horizontal components, the two first components together, and then I'd add it to what I get when I multiply the two second components together. So it's really pretty easy to get. So in this case, U dot V is going to be, I take the first two and multiply those together, so that's going to be 2 times 5, plus what I get when I multiply these two guys together, so that's going to be 3 times negative 2. So this is 10 minus 6. The dot product of U and V in this particular case is 4. Now, one of the uses of the dot product is it allows us to help find out what the angle is between two vectors. So we're going to go over a formula that can be derived using the law of cosines. And if you're interested in the derivation of this particular formula, it's actually quite interesting. You can find several of them on the internet. And if you want to send me an email, I've got a couple that I think are particularly good. But we won't worry about that in this course. But if you are interested, we could find those. So what I want you to note is this formula is different than the one that it shows in the textbook. In the textbook, I believe it shows that the cosine of an angle is A dot B over magnitude of A times the magnitude of B. Well, if we're going to find the angle, I'd rather just solve for the angle. So all I did is just take the cosine inverse of both sides, but just realize that that's the way that it shows in the book. So the angle between two vectors is going to be the cosine inverse of A dot B over the magnitude of A times the magnitude of B. And so we could say it this way. We could say the angle between two vectors is the cosine inverse of the dot product over the product of the magnitude. So a nice little phrase that will kind of help you remember how that works there. So another thing that I want you to note is that cosine inverse has a range from from 0 to 180 degrees. So it's always going to give you an angle between 0 and 180. Nice advantage there. Think about law of sines and sine inverse and stuff like that. So really a nice advantage of this little formula right here. So let's take this problem right here. Let's take the one that we did up above, and let's find the angle between U and V. Well, I mean, one way you could do this is you could try and draw a picture, and it is possible to do that. But let's just blindly go through and let's use the formula. So this is going to be the cosine inverse of, and remember, it's the dot product, which we already found the dot product up here. The dot product was 4. Now we need to find the product of the magnitude. So I've got to find the magnitude of each one of these. So the magnitude of U is going to be the square root of 2 squared plus 3 squared. So that's the square root of 13. And then the magnitude of V is going to be the square root of 5 squared plus, if you want to do negative 2 and square that, that's fine. So we get 25 plus 4, so that's going to be the square root of 29. So I get radical 13 and radical 29. And then I'm going to have the calculator figure this out for us. So let's grab the calculator. We'll make sure we're in degree mode, which we still are from last time, I believe. Yep, we're still in degree mode there. And then we're going to type this in here, and we're going to see what the angle between these vectors is. So we're going to do cosine inverse 4 divided by. Now, I need to divide by all of that, so I'm going to put the denominator in parentheses. So this is square root 13, close the parentheses, times square root 29, close the parentheses and close it one more time. That's the 4 divided by both of those magnitudes, the radical 13 and the radical 29. I hit enter, and I get 78.1. 78.1 degrees. Well, if we were to draw the two of these, so again, over 2 and up 3, so here's vector u, and vector v was over 5 and down 2, so it looks like this. What this just did is it found this angle right in here, okay? It's not gonna find the outer one. You could do that by subtraction. It's always gonna give us an angle between 0 and 180 degrees, okay? So that looks about right, okay? The last idea that we're going to talk about in this section is the idea of unit vectors. And then we'll do a couple problems for practice after we're done with this. So unit vectors are vectors that are, I mean, just like the name describes, they are vectors that are 1 unit, looks like I don't have enough spaces here, 1 unit in length. Okay, or 1 unit long. Okay, so they're all 1 unit long. And we've got a couple standard unit vectors. The vector I is 1, 0, and you can tell that's 1 unit long. You could throw that into our little formula for the magnitude. It only has a horizontal component of 1 and no vertical component. And then J is 0, 1. So here's what they look like if I were to graph them. I'd have 1 unit in this direction for I, and I'd have 1 unit in this direction for J. All right. So there's vector I, there's vector J. And the reason we do this is there are quite a few reasons, but let's just run through a couple of them. So the first thing is they provide a coordinate system. So you'll notice that vector I is over here, and I kind of labeled this as I, and J is up here and labeled that as J. So we've kind of been skirting around this issue and talking about, okay, horizontal, and I've even slipped up and called it an X coordinate and stuff like that. Okay, if we use I's and J's, everybody will know we're talking about vectors instead of kind of saying, oh, it's kind of like X and kind of like Y. So if we use I and J, everybody knows that we're using vectors. So it gives us a standard notation and it provides a coordinate system for us. Okay. The next thing is unit vectors that are in common directions are easily recognized. So let me give you a unit vector. A unit vector 1/2, radical 3 over 2. So take a look at that. That is a unit vector. We can verify that it's 1 unit in length because I could square this one, I'd get 1/4. I could square that one, I'd get 3 over 4. Take the square root of that, I'd end up with the square root of 4 over 4, so that is 1 unit in length. So it's 1 unit long, okay? And if you take a good look at it, if the horizontal component is 1/2 and the vertical component is radical 3 over 2, you also know what that angle is right there. That angle would have to be 60 degrees, okay? If I wrote another one like negative radical 2 over 2, radical 2 over 2, okay? That's another one that would be 1 unit long, okay? It would be on the unit circle, so by definition, the magnitude of the radius would be 1, and we could quickly figure out what the angle is. So it has that nice advantage. The next thing is we can rewrite any unit vector in terms of the standard unit vectors. So this is 5 for a horizontal, so I'd go over 5 in the I direction, and I'd go down 2 in the J direction. So I can write that as 5I minus 2J, okay? And sometimes we'll call this a linear combination of the standard unit vectors, okay? So there's another way to write a vector other than just having it in component form, okay? Vectors that are 1 unit in length are generally easier to work with just because they are 1 unit in length, okay? And they're also useful in calculus, so you'll just kind of want to keep those things in mind. So let's take a look at a problem here, and let's run through and do this. So you have problems like this on your assignment. It says, Vector v is 4 comma negative 3, and we want to write that as a linear combination of I and j, and then we want to draw a geometric representation of that linear combination. It is literally this easy. Vector v is 4, I is in the horizontal direction, so 4i, and then minus 3j. So you're literally just taking this, putting an I on it, taking that, putting a j on it, and then just putting the two of those together. So that's what we'd have as a linear combination, kind of like what we did up here, as I mentioned earlier. And then let's talk about what would a geometric representation of this look like. So this would be 4 i's minus 3 j's. Well, I is in this direction. This would be positive I, and this would be negative I, and positive j and negative j. So I'm going to have 4 i's. There's 1, 2, 3, 4. So there are 4 of these little standard unit vectors of I represented. Okay, and then I want minus 3 j's. So minus 1, 2, 3 j's, and here is the result of adding those vectors together. So if I have 4 i's and minus 3 j's, there's my vector of 4, negative 3, 4, negative 3. Same thing there. Okay, and then it says find a unit vector in the direction of v. So a lot of times we're interested in figuring out which direction something is going so that we can match it, and we normally do that in terms of a unit vector. So if this right now is this vector, this blue vector right here, I want one that heads in exactly the same direction but is only 1 unit long. So I want it to be about right here. Well, if this is the original vector, and I wanted it to be 1 unit long. Well, what I could do is I could shrink that down to size. So the first thing we'd want to do is we'd want to figure out, well, what's the magnitude of v? Well, that would be 4 squared plus negative 3 squared, so that would be 5. So if right now this is 5 units long and I want to shrink it down to be 1 unit long, it should make sense that I'd take this and divide it by 5 or multiply it by the scalar 1/5. So I end up with 4 over 5 comma negative 3 over 5. Okay, that's what it would be in component form. If we wrote it as in the standard unit vectors i's and j, that would be 4/5 I minus 3/5 j. Okay, so that would be a unit vector that would be in the same direction as v. So 1 unit long, but in the same direction as v. And if we take a good look at this, so we're looking for 4/5 comma negative 3/5. So 4/5 would be about right here. Negative 3/5 would be about right there. Looks about right. And if you wanted to plug that into the magnitude formula, so square root 4/5 quantity squared plus negative 3/5 quantity squared, you're going to end up with 16/25 plus 9/25. And of course, that's going to give you 25/25. And taking the square root is going to give you 1. Okay, so those are all the ideas. Now let's just hit a couple of practice problems and kind of firm up a couple of things. So problem number 4 says, for each pair of vectors a and b, draw the vector a plus b and a minus b. So here's vector a and here's vector b. So if I want to add those together, here's what I'm going to do. I'm going to draw a copy of this one up here. So again, I'm going to draw that parallelogram or that tail to tip method. So this is over 5 and up 2. So over 5 and up 2. So here's a copy of b. And if I wanted to draw a copy of a over here and do the parallelogram method, remember, the resultant goes from the tail of both of them to the tip of both of them, or the tail of the first one to the tip of the second one. So that's what we've got right here. This would be a plus b. There's vector a plus b. Okay, now, if I want to do a minus b, remember, minus b goes in the exact opposite direction. So instead of going forward and up, we're going to go back and down. So it's going to look like this. We're going to go back and down. So here's what minus b would look like. So the resultant would go from the tail of the first one to the tip of the second one. So that would look like this, and this would be A minus B. So I've drawn the resultants in green, but that's what you'd get there. Now we could check this. You could figure out what these each were in component form and then figure out what you get when you add them together and when you subtract them together, but they don't ask you to do that. So we won't bother with that here, but that's how we geometrically represent the addition and the subtraction of those two vectors. And then later on in the assignment, you've got some problems that hopefully are pretty darn easy. Vectors take a little bit of getting used to them, but once you get used to them, they really have some nice advantages. So here we're going to take this vector, and this vector, r, s, and t, and we're going to perform this operation. So we're going to take r and we're going to subtract what we get when we add s and t together. So you could think about drawing these three vectors, moving them around, doing the tail to tip method or the parallelogram method in order to figure out what their resultant is when we put them together. Or we can just do this. We're literally taking r, which is 3 comma negative 2. There's the horizontal and vertical component. And then we are subtracting what we get when we take s, 1 comma 5, and add 4 comma negative 6. Well, the great part about this is just like kind of like regular old distributing. So this is going to be 3 comma negative 2, and then I'm going to distribute that through. The last one I left the negative here. This one I'm going to go through and put these together. So this is going to be, well, let's figure out what we get here. If I add these together, I get 3 comma negative 1, because that's a negative 6, right? Yep. Okay, so I get 3 comma negative 1 when I add those together. And then if I subtract that, I'm going to have a minus 3 and I'm going to have a plus 1. And then I can just put these together, so I get a 0 and a negative 1. So there is the resultant. I don't have to draw any pictures or anything like that. I can just put these together component by component. I get a 3 comma negative 1, and then I can subtract that or just add the opposite of this guy right here, which is what I did. And you'll notice that we've got a unit vector here. And if I were to write this as a linear combination of the standard unit vectors, which they don't ask you to do, it would be no i's and then minus a j. But again, they don't ask you to do that, just extra application there. Okay, now you do have some problems that are kind of interesting. You could solve these several different ways. And they talk about the angle between vectors. Again, got to get used to working with that formula. Don't be surprised if you see something like that on the test or on the final exam. So a couple of thought questions here. Just remind yourself, what is the cosine of 90 degrees? Cosine of 90 degrees, that's going to be 0, okay, because we're right here on the unit circle. X coordinate would be 0. Okay, so the cosine inverse of 0 is 90 degrees. So if you think about this, the only way that the cosine inverse of the dot product of the vectors over the product of the magnitude of the vectors could be 90 is if this ends up being 0. And the only way this whole fraction right here can be 0 is if this right here is 0. So the only way that we're going to get two angles to be 90 degrees from one another, or in other words, they're going to be perpendicular from one another, is if the dot product equals 0. Okay? So if the dot product is equal to 0, then get rid of that. If the dot product's equal to 0, then the angle between them would be 90. All right, we're back up and running with the battery. Okay, if we wanted to tell if two vectors were perpendicular, all we'd need to do is check and see what their dot product is. If their dot product is 0, then we know the two of those meet at a 90-degree angle. Well, let's think about what it would mean for two vectors to be parallel. Well, normally we consider parallel to be lines that don't cross. But in this case, think about what would happen here. We could have a vector heading off this way and another one heading in exactly the same direction. Now, whether they're right on top of each other, that part about it, we don't really care. We kind of want them to be headed in the same direction. Or what if they were headed in opposite directions? Okay, we could still consider those parallel. Well, let's think about this. If they're headed in exactly the same direction, okay, the angle between them would be 0. And if they're headed in exactly the opposite direction, then the angle between them would be 180. So the cosine of 0 is 1, and the cosine of 180 is -1. So we're interested in when we use this little formula, cosine inverse of the dot product over the product of the magnitudes, we're interested in that turning out to be either 0 degrees or 180 degrees. Either one of those, we'd say that would be parallel. So let's think about that for just a second. How could I get this to turn out to be 0? Well, what I'd have to plug in here would either be a 1 or a -1. So let's think about that for just a second. Okay. One thing we could do is we could just compare the components. So if one of them is heading off in this direction, it's made up of two components like this, and the other one is heading over here and then a little bit longer or maybe a little bit shorter, okay, we could just compare the components. Or you could think about that, maybe think about the slope that it would be. So in order for them to be parallel, the two vectors must be scalar multiples of each other, okay? And we could even have one that's the same length but heading off in the other direction, okay? So they've got to be scalar multiples of each other. Or we could use the dot product, okay? And in order for this to work out to be 0 or 180, this has either got to be a 1 or a -1. Well, the only way it could be a 1 is if the top and bottom are exactly the same, or they're exactly the opposite. So the dot product and the product of the magnitudes must be the same or opposites of each other. Okay? So let's take a quick look at an example. It says determine whether the vectors are parallel, perpendicular, or neither. So let's look at, so we've got -2, 3 and 6, 4. So I'm going to use the formula here. So the angle is the cosine inverse of, it's the dot product. So let's find the dot product. That would be -12 plus 12. So I get a 0 here. Okay, doesn't really matter what the magnitude is here or the magnitude there. Okay, clearly they have some length, so we're not dividing by 0. So if I've got a 0 in the numerator, again, let's just double check that, make sure. If I do cosine inverse of 0, I end up with 90 degrees. So that's 90 degrees, so we would say those are perpendicular. Okay, let's try this one. This one would be the cosine inverse of, if I do a dot product, I get -8, and I get plus, let's see what we've got here, plus 18. So this is going to be 10. And then I've got to find the product of the magnitudes. So the magnitude of this one is 4 plus 9. That's going to be 13 for the first one. Write down a little bit of work for that. -2 squared plus 3 squared, square root of 13. And this one would be 4 squared plus 6 squared. So that's going to be, pardon me, let's see, 36 plus 16, so 52. Let's see, there's no way that's going to be 10. No way that's going to be 10. So these are not exactly the same, and they're not exactly the opposite. So this is not going to be parallel or perpendicular, but let's just double check this and just make sure. So I'm going to do a cosine inverse of, we're going to do 10 divided by, and again, we'll start a set of parentheses, square root of 13, close the parentheses there, square root of 52, is that there, and I get 67 5.4 degrees. Okay, not parallel, not perpendicular. So we'd call that neither. Okay, couple things that we just want to note. The word orthogonal, you'll hear that occasionally. That means perpendicular. Okay. Normal is another word that also means perpendicular. They're pretty much used interchangeably. So if you were talking about an orthogonal lines, perpendicular lines, or normal lines, all of those would be perpendicular. You just want to, they meet at 90-degree angles. You want to be aware of the vocabulary there. Okay, and you could find these answers up above by just thinking about the slopes of each one of those position vectors and then comparing those. But I'd really encourage you to use the formula because that formula has a lot of applications in the future. So you'll want to be aware of that. And then the last thing I want to make you take note of in this section is this is just a basic understanding and a basic outline of some of the properties of vectors and some of the things that we can do with vectors. It's going to be really important that you understand how those vectors work because those ideas are going to be used in the next section. We're going to be solving some fairly complicated problems with those. So if you'll get used to section 5.4, ask questions about it, make sure you can do the problems. You should be in good shape for the exam, but more importantly, you're going to be in good shape for the next couple of sections because the ideas, again, build on each other and they're very, very similar. So please make sure you practice this enough, ask questions. You're going to see this again in the future, and much easier to do those future problems if you've got this understood. So thank you very much.